Number 9. If the terminal ray of an angle theta is in standard position, passes through 1, negative 2, find sine theta and cosine theta. So when it comes to doing trigonometry problems, what I really recommend you doing is drawing the unit circle. Always try to visualize what's going on here. And it just needs to be a sketch, nothing too fancy. So in this case, we have the point 1, negative 2. That places us in quadrant 4 because we know that we go 1 to the right and negative 2 down. So we're going to have an ordered pair somewhere around here, and that ends up creating a terminal ray somewhere along this location here. And because we have the terminal ray here, what you see is that the angle that's formed as we go counterclockwise looks like that. But really, in terms of its reference angle, you create the reference angle that's formed right here. Remember that the reference angle is always in line with the x-axis, and it's acute. So what you'll notice is that with the reference angle, you can actually develop a right triangle out of this. And with that right triangle, it allows us to find all the parts of the triangle, specifically the length of this radius here. Oops, I'll redraw it. The length of this radius here. And so to find this length of the radius, you can just use Pythagorean theorem, where r is equal to the square root of 1 squared plus negative 2 squared. And then therefore r is equal to the square root of 5. Keep in mind, it's always going to be a positive value here. You know that with the Pythagorean theorem, if you were to square root both sides, you should end up with a positive negative. But because we're actually talking about the length of a radius of a circle, right? Imagine that this is actually a circle. This is the radius of a circle. And so because we're talking about the radius, it should only be a positive value. So keep that in mind. Okay, so anytime you ever find the diagonal here, the radius, it should always be a positive value. And now we can actually set up our trig ratios where we recall that sine of theta is equal to opposite over hypotenuse. Now on this particular triangle, as we take a look at our angle theta, opposite our angle theta is that value of negative 2. So sine of theta is equal to negative 2 over the hypotenuse, which we just found, the hypotenuse being the square root of 5. And after you rationalize everything, you should get negative 2 square root 5 over 5. Another trig ratio we need to find is the cosine of theta, so we're just going to go ahead and set that up here. So cosine of theta, recall that trig ratio is the same thing as adjacent over hypotenuse. And so the adjacent side in this case of our angle theta is going to be the value of 1 over the hypotenuse, which again is the value of root 5. And so when we rationalize again, cosine of theta is equal to root 5 over 5. Now, as we take a look at our two results, notice the signage of both of them. Remember our mnemonic in a previous video of saying that for trig ratios, we want to remember the A, S, T, C. And because we are in quadrant 4, only cosine should be the trig ratio that is positive. And in fact, we see that it is a positive value here. And because we are in quadrant 4, you should just make sure, double check, is your sine a negative value? Because only cosine should be positive here. And indeed it is. Okay, let's go on to the next page. Number 11. Solve cosine of theta equals 0 for theta in degrees. So again, it always helps to visualize it. Draw a coordinate plane. We're going to have our unit circle here. Now, recall in a previous video how we said that the ordered pair x, y anywhere along the circle can also be represented through its angle measure, and we set up that angle measure as seeing that that was cosine theta, sine theta. So in the case that we see here, if we're trying to find when cosine of theta is 0, this is basically asking us when does this ordered pair have a 0 in the x-coordinate, and then, whatever else in the y-coordinate, we don't really know. But in the case that we have here, our unit circle drawn out for us, we see that 0, that's always going to occur along the y-axis. So we have a point there at the top and a point at the bottom. Right, that would be the point 0. Actually, with this being the unit circle, this would be the point 0, 1, and this would be the point 0, negative 1. Well, when does that occur? In order to get to that point, remember, if you start at the starting position, you have to go 90 degrees. So really, we're seeing that we have a 90-degree angle, and then we also have going all the way around here, That would be a 270-degree angle. Okay? Now, there's also nothing to stop you from saying, well, just because I reach the 90-degree angle doesn't mean I just can't keep going in a circle because a circle is never ending. If I go in a circle and make my way all the way around, I'll be back in the same position at 0, 1. So not only do I have a 90-degree angle, but I can add 360 degrees to it. And I can keep adding and adding and adding. So I can add 360 degrees some number of times. Let's call it n number of times. And n has to, you need to make sure that n represents an integer value because it has to go around a full revolution. If you only go around like a quarter of a revolution, you're not going to hit the same spot. So that's why it's important we add the 360n. Okay? Likewise, if we're at 270 degrees, oops, I just erased everything. Undo. Sorry, I'm just trying to erase the green here. Nope, it's not going to work. Nope. All right. Let's just do it all over then. So if we're at, if we are at 270 degrees, we can go around another full circle and another full circle and so on and so on. So therefore we can add another 360 degrees n. So these would be the two responses that you can use to get cosine of theta equals 0. Or if you really want to consolidate everything, here's our circle again. If you really want to consolidate everything, what we can say is that if we reach the 90-degree mark, technically we could just add 180 degrees to get to the next mark. And then add another 180 degrees to get to the next mark. And then add another 180 to get to the next mark, and so on and so on. So if you want to join these two answers together, you can really say that you start at the 90-degree mark, but you always add 180 degrees every time. And the only way we can add 180 degrees is if they're represented by full integer values, again, so 180n, where n is an integer. So this one answer here would consolidate the two answers that we have right here. So this would be like an OR. All right. So let's go on to reciprocal trig functions. Evaluate sine of 3 pi over 4. So sine of 3 pi over 4 would mean that takes us to quadrant 2. Right, here's 3 pi over 4, something like that. And so if we want sine of 3 pi over 4, keep in mind that with our mnemonic again, A, S, T, C, sine is positive in this area here. So we can go ahead and find sine of 3 pi over 4 by understanding what its reference angle is. Its reference angle from 3 pi over 4 in quadrant 2, that'll give us a reference angle of pi over 4. And so therefore, sine of 3 pi over 4 is really equivalent to sine of pi over 4. And because we're in quadrant 2 where sine is positive, we still have a positive value attached to this number here. And sine of pi over 4 is the same thing as square root 2 over 2. So it's a positive square root 2 over 2. Likewise, if we take a look at 1 over sine of 240 degrees, you'll notice now that with the 240 degree angle, that's now going to put us into quadrant 3, right? Something like this. Okay, and remember that we need to convert the 240 degrees into its reference angle. Well, we know that we go an entire 180 degrees and then we have some left over. How much left over is that? Well, 240 minus 180 is going to give us a 60-degree angle that's left over. So therefore, we know that the reference angle is 60 degrees. So this is equivalent to 1 over sine of 60 degrees. Keep in mind your mnemonic. Because you're in quadrant 3, only tangent should be positive here, which means the sine value is actually going to be a negative value. So from here we can go ahead and simplify. This is the same thing as 1 over negative. Sine of 60 degrees is the same thing as square root 3 over 2. And because you have a fraction divided by a fraction, that's equivalent to saying negative 2 over root 3. And then of course we need to rationalize this. And so we get the value of negative 2 root 3 over 3, like that. Okay. All right, so the reason why we have number 1 and number 2 is kind of showing us how eventually we're going to end up having to see the trig ratio you'll see here in the denominator of a fraction, and this is what we call the reciprocal trig functions. Now, when it comes to actually representing what the reciprocal trig functions look like, we go to this diagram here. Now in our circle here, not exactly a unit circle, but in our circle here, we know that we're going to have a right triangle again that we can always develop with an x value, a y value here as a vertical, and an r value, the radius, not exactly being a unit, so it can be any radius value. With that in mind, our trig ratios would show us that sine of theta, here's theta, is equal to opposite over hypotenuse, so y over r. Cosine of theta is equal to x over r, and tangent of theta is equal to y over x. Now it turns out that what we've just done in the previous example was looking at reciprocal trig ratios, and right here, these next three ratios that you see here are our reciprocal trig ratios. So CSC theta represents what we call cosecant theta. And cosecant theta is the same thing as 1 over sine theta. And that's the same thing, therefore, as r over y, because this is reciprocal. SEC theta is the same thing as secant theta, which is the same thing as 1 over cosine theta, which, if you look at cosine, that's the reciprocal of that, which is r over x. And the next one is cotangent of theta, tangent of theta, which is 1 over tangent. And that's the same as x over y. Or you can also think of it as cosine over sine. If tangent was sine over cosine, then cotangent is cosine over sine. Okay, so those are basically our reciprocal trig functions, and you can apply it the same way that you would with any other trig functions. For example, if you have a cotangent of 290 degrees, then thinking about where that is, 290 degrees would place us right here, right? And because it's going to place us in quadrant 4, if we want the reference angle, this right here would be its reference angle. Its reference angle is 360 minus 290, which would give us 70 degrees. So our reference angle is 70 degrees. So in terms of the reference angle, cotangent of 290 degrees is really the same as cotangent of 70 degrees. But because, just like our mnemonic before, only cosine is positive in quadrant 4, therefore tangent is negative. And so therefore its reciprocal cotangent is also a negative value. So this would be negative cotangent of 70 degrees. Okay? And that concludes 6.2.